April 8th. Lesson 21 and Lesson 22, the method of undetermined coefficients and variation of parameters. In the last lecture, Monday's lecture, we went over case 2 and case 1 for the function q of x that was on the right-hand side. Case 3, if you recall, case 3 occurred when the function on the right-hand side shared a factor with one of the terms appearing in the solution to the associated homogeneous equation that corresponded to a repeated root of the characteristic polynomial. Before, we only considered cases in which the function q of x shared a factor with a solution of the associated homogeneous differential equation that corresponded to a root of the characteristic polynomial that was not a repeated root. So we'll see how that works in this lecture. We'll also see for more general functions q of x, and actually for second order ODEs, any function q of x will work. This method will work, the method of variation of parameters. Now will work, it is to be used when the function q of x in the non-homogeneous differential equation has infinitely many linearly independent derivatives as opposed to only finitely many. We'll begin with case 3. Suppose q of x, the function on the right-hand side of the non-homogeneous equation, has a term that's x to the k times u of x. Here u of x is a term of the complementary function, the function that is the general solution to the associated homogeneous equation, and that corresponds to a repeated root of p of r, the characteristic polynomial, that has multiplicity m. The particular solution in that case will consist of a linear combination of x to the k plus m, so remember in case 2 is x to the k plus 1, times this term of yc, and its linearly independent derivatives, plus possibly other terms that were obtained from case 1 and case 2. Again, as in the case of case 2, we exclude terms that already appear in the solution yc of the associated homogeneous differential equation. I think this is best seen with an example. Solve y double prime minus 2y prime plus 1 is e to the x. In this case, the characteristic polynomial is r minus 1 squared. R minus 1 squared means 1 is a repeated root of multiplicity 2. You're raising this factor, r minus a number, to the second power. That's where we get multiplicity 2 from. We've seen in last week's lectures that we can obtain a solution of the homogeneous differential equation, where this e to the x is replaced with 0, c1 e to the x plus c2x e to the x. q of x is just x to the 0 times the first term of yc, ignoring this constant parameter c1. That means yp, the particular solution, will consist of linear combinations of x to the 0 plus 2, so 0's from here, that's just how we wrote q of x, and 2 is from the multiplicity of the repeated root, in this case 1, of the characteristic polynomial. So it consists of linear combinations of x to the 0 plus 2 times e to the x squared times e to the x, and its linearly independent derivatives. The derivative of x squared e to the x is 2x e to the x plus x squared e to the x. The second derivative of x squared e to the x is 2 e to the x plus 4x e to the x plus x squared e to the x. There are 3 linearly independent terms that are appearing: e to the x e to the x, and x squared e to the x. But the first 2 already appear in yc. we throw those away. We throw e to the x and x e to the x away. What are we left with? We're just left with x squared e to the x. If we're just left with x squared e to the x, well, that makes yp actually a pretty simple function. Just going to be a constant times x squared e to the x. And we go through the 3 steps we saw in Monday's lecture. Set the particular solution equal to a unknown constant, an undetermined coefficient, a times x squared e to the x. You plug this yp back into the ODE to get 2a. You can check this just from differentiating. All the other terms go to 0. You're left with 2a e to the x is e to the x. So the system is just one equation. 2a is equal to 1. Solve for a. You get a is 1/2. And your particular solution is 1/2 x squared e to the x. General solution, just add this particular solution to the general solution we found. c1 e to the x plus c2 x e to the x plus 1/2 x squared e to the x. So again, what's important to remember is that, as you've seen in last week's lecture, in linear differential equation of order n that's homogeneous, will always have linearly independent solutions. And those correspond to roots. Each of those corresponds to roots. Sometimes one root gives you 2 solutions, as in this case, of the characteristic polynomial. All those solutions will correspond to roots of the characteristic polynomial. Now we'll discuss the method of variation of parameters. If q of x has, so now if the function has an infinite number of linearly independent derivatives, for example 1 over x, the method of undetermined coefficients won't work. That's because the method of undetermined coefficients only works when you get terms that will cancel and when there's finally many linearly independent derivatives. So eventually you keep differentiating the function, you'll get 0, or you'll get functions that you've seen before. If you differentiate 1 over x, x to the negative 1, you get x to the negative 2 up to a constant multiple, x to the minus 3, x to the minus 4. Those are all different linearly independent functions, and that keeps going on forever. Minus 4, minus 5, all the way, can keep counting down to minus infinity. For simplicity, in today's lecture, we'll discuss the second order nonhomogeneous ODE. a2 times y double prime plus a1 y prime plus a naught is equal to q of x. Here we're going to use variation of parameters. First step is to find 2 linearly independent solutions, y1 and y2. We've seen this. We can always find these from the characteristic polynomial and of the associated homogeneous ODE. So we can always find these 2 solutions. Next, we're going to set a particular solution. So it's similar to the method of undetermined coefficients in the sense that we set up a form of the particular solution. In this case, however, instead of just looking like q of x and its linearly independent derivatives, or maybe x to a power times times a term in q of x and its linearly independent derivatives, it looks like u1 of x times y1 of x plus u2 of x times y2 of x. So u2 of x and u1 of x can be thought of as functions parameters. u1 of x and u2 of x are unknown functions to be determined later. That's why instead of undetermined coefficients, it's variation of parameters. u1 of x and u2 of x are the parameters in this case. Again, as in the method of undetermined coefficients, we plug back in this form of the particular solution to the original ODE. We get this equation. Now it turns out the last 2 terms, if you look at them carefully, each of them, the second to last term contains this factor, u1 prime times y1 plus u2 prime times y2 prime. The last term also contains the factor u1 prime times y1 plus u2 prime times y2. The factor here in the second to last term differs from the factor in the last term just by taking a derivative. So it actually turns out to be simplest if we just set this term equal to 0, identically 0. If it's the function 0, its derivative is also 0. That makes these last two terms vanish. And then all we're left to do is solve a2 times u1 prime y1 prime plus u2 prime y2 prime is equal to q of x. We're going to solve that for u1 prime y1 prime plus u2 prime y2 prime. And we can always divide by a2, right? Because this is a second order non-homogeneous ODE. Because it's second order, the coefficient of y double prime has to be non-zero. We can always do this. For second order ODE, we can always solve for u1 and u2. We'll see how that works in the next slide. And we can just plug these back into YP and get, voila, we have our particular solution. Here's how we solve the system. We have this system of two equations, u1 prime y1 plus u2 prime y2, 0. u1 prime y1 prime plus this should have been u2 prime y2 prime is q of x over a2. This can be solved for u1 prime, and u2 prime. u1 prime is negative q of x y2 over a2 times y1 times y2 prime minus y2 times y1 prime. u2 prime is q of x times y1 over a2 times the same factor. So the denominator in each case is the same. The numerator just changes from minus q of x times y2 to q of x times y1. So you'll actually see later this denominator here a2 is a2 times what's called the Wronskian of y1 and y2. And it turns out that Wronskian, y1 times y2 prime minus y2 times y1 prime, is never 0 provided y1 and y2 are linearly independent. Well, that was a requirement. First, just find two functions that are linearly independent. Non-homogeneous differential equation of order 2 will always have one, provided it's linear. And that means this factor here will not be 0. So this denominator is not 0. u1 prime is a function, u2 prime is a function. Just integrate. You get u1 and u2. Voila, you have u1 and u2. That's always going to be the case. Now, sometimes it's true. You might not be able to write u1 and u2 if q of x is some crazy function. u1 of u2 might not be able to be written in that nice of a way. Even if actually q of x is a pretty simple function, like 1 over x, it's still possible that u1 and u2 are still functions, but they are not really written in closed forms. They are not be recognized in terms of elementary functions that we've seen. But in certain cases, special cases, these will be nice functions. You can integrate them, and you will get nice elementary functions as well. Let's go over an example. Solve y double prime minus 3y prime plus 2 is equal to e to the x over, okay, this actually should have been cosine of e to the minus x. We'll see that in a second. And here, r squared minus 3r plus 2, this factors into r minus 2 times r minus 1. And the complementary solution is c1 e to the x plus c2 e to the 2x. y1 is e to the x, y2 is e to the 2x. We set up u1 of x times e to the x plus u2 of x times e to the 2x. So again, this was a mistake. This should have been cosine of e to the minus x. If you plugged in this, you could still solve for u1 and u2. It's just they wouldn't be written in nice elementary functions as in this case. Into the original ODE and get this system. This is just the system that's obtained from plugging in YP in the original ODE. It's simplest to get this system. So remember here that it's always u1 prime times y1 plus u2 prime times y2. And this is the same thing, but now y1 is replaced with its derivative. Here, the derivative of e to the x is just e to the x. y2 is replaced with its derivative, in this case, 2 e to the 2x. And differentiating e to the x is usually pretty straightforward. So that's why method of variation parameters can be pretty straightforward, provided you solve for u1 prime and u2 prime. Step 4, solve this system. u1 prime, so if you do some algebra, u1 prime is minus e to the minus x cosine e to the minus x. u1 of x is sine e to the minus x. And what do we get? u1 prime is e to the minus 2 cosine of e to the minus x, or negative e to the minus x times negative e to the minus x cosine negative e to the minus x. You integrate this, you get negative e to the negative x sine e to the negative x minus cosine x. I won't go into the details here, but you can check for yourself. This is just integrating minus e to the minus x cosine of e to the minus x. It's obtained from integration by substitution. Integrating this, first we substitute, and then we do integration by parts. You can check that this works. The substitution here is u is e to the minus x, and this becomes, so this is pretty straightforward. This becomes just antiderivative of cosine u, which is sine of u is e to the minus x, replace u with e to the minus x. Here, you have to first do u substitution. U is e to the minus x, du is minus e to the minus x, dx. So this becomes integral of minus u cosine of u. Anti-differentiating using integration by parts, you get minus u sine u plus minus cosine u. And then just replace in u is e to the minus x. So this is just algebra. Plugging in, okay, now yp, what is yp? It is u1 e to the minus x sine e to the minus x times y1 e to the x plus y2 e to the 2x times u2 minus e to the minus x sine e to the minus x minus cosine x to the minus x. So this might look a little messy, but it does simplify pretty nicely to this function, negative e to the minus 2x cosine e to the minus x plus 1 minus e to the x times sine e to the minus x. Here's the general solution. c1 e to the x plus c2 e to the 2x minus e2 e to the 2x cosine e to the minus x plus 1 minus e to the x cosine e to the minus x. So again, all that was just plug in this particular solution, same as always. Once you get a particular solution, add that on, tack it on at the end of the general solution. And that's all for today. So I'll see you all on Friday. We'll discuss, in that case, variation of parameters for a higher order linear differential equation with constant coefficients. And again, the same case for q of x. In that case, it's actually very similar. We get a system. It's a system of in this case, it's a system of inequations in unknowns u1 prime through un prime. We'll discuss that more on Friday.